Hi, in this video we'll continue our discussion on Introduction to Software Engineering. In the previous video we saw that there's three ways in which we can deal with software complexity: abstraction, decomposition, and hierarchy. And the inherent nature of software is that it's complex. Its requirements are constantly changing. It provides extreme flexibility, with all of these constraints, we want to make sure that high quality software is produced within a given budget and within a given time frame. But then with all of these conditions, and very often the application domain that the software belongs to is a complex domain, and that's the reason we need different techniques to be able to deal with this complexity. In the previous video we saw that through abstraction, basically by creating different kinds of models, we can better understand the software system. In this video we'll look at decomposition and hierarchy. So decomposition is basically a technique wherein we want to master complexity through this divide and conquer technique. So basically break down the problem into smaller pieces, solve those smaller pieces, and then put those pieces back together to form the whole. That's the idea. Now decomposition again can be done in two different ways. The first one is functional decomposition. So basically the idea is to now think in terms of functionality of the system and break it down based on that functionality. So decompose the system into smaller modules where each module handles a function. So it's one major processing step in the application domain. So and the modules can then further be broken down into smaller modules, and we continue doing this as far as we can go to get to that smallest module possible. And then we solve that smallest piece first and then build our way back up. That's the idea with functional decomposition. The other one is object-oriented decomposition, and the idea here is to basically take the system and break it down into classes or objects. So think in terms of objects, and we want to decompose it into these different objects. Now each class is basically a major abstraction in the application domain, and when I say abstraction, it's one of those major concepts that's used in the application domain. And classes also can be decomposed into smaller classes. So these are the two different ways in which decomposition could be done. So which decomposition is the right one? Now we could argue, is it functional or is it object oriented? But really I would say that the right way to go about is do both. Do both functional decomposition and object oriented decomposition. Think of the functionality as well as how do we break up the system in terms of objects, and that's the best way to deal with the software complexity. Let's look at an example of functional decomposition. So say there is one high level system function, and our goal is to break that down or decompose it into smaller sub functions. So every function can be thought of reading, so the process can be thought of as reading an input and then performing some kind of processing on that input and transforming it, and then finally producing an output. So we basically break down this high level system function into three sub functions of read, transform, and produce output. So that's the first level of decomposition, and then we can continue doing this till we get to the smallest possible function. So we again break down read further down into, say, three smaller sub functions. Similarly, transform is broken down, and then the produce output is broken down into smaller functions, and we keep doing this till we get to that lowermost level of, say, machine instructions. I mean, in this programming world, that's the lowermost or the simplest possible instruction would be a machine instruction, say load a register or add contents of two registers. So that's the idea of decomposition, functional decomposition. So in a flight reservation system, basically we start at that highermost level function, which is making the reservation, and then it can be broken down into these smaller functions, and we keep going, we keep decomposing till we get to that smallest possible functionality. So that's the idea with functional decomposition. Why is functional decomposition important? The reason for that is functionality is spread all over the system, and if there is a maintainer of the software, then they need to have a good understanding of the entire system. If an enhancement needs to be made, or if we come across a bug and if something needs to be fixed in the system, the maintainer needs to know where this change has to happen, and in order to be able to make that change, he or she needs a good understanding of that entire system, and functional decomposition is one way to gain a good understanding in that way. Also, code is usually hard to understand. It is complex and it's very difficult to maintain. So these kind of techniques help with that. User interfaces, they are awkward and non-intuitive as well if you look at the code behind the scenes for user interfaces. So again, this kind of a functional decomposition helps with that too. So it's useful when we are building software from scratch and we are trying to come up with a design, but it's also useful when we are dealing with existing software systems and maintenance of those existing software systems. So we'll use the example of Microsoft PowerPoint's AutoShapes. The AutoShapes software has the functionality to draw different kinds of shapes, and there is the ability to change them, to color shapes, to change the color of borders, to change the border widths, and so on and so forth. Say the software already exists and then there is a problem with one particular kind of shape, and if the programmer needs to update that, it's a huge software system. The PowerPoint's AutoShapes in itself is huge, so being able to identify where that change needs to be made is not a trivial task. Or say if we want to enhance AutoShapes and add a new shape to it, there is existing functionality already out there to be able to draw a shape, to change it, to color it. We want to reuse all of that code as much as possible and then add this new shape to it. So again, over there, the programmer needs to have a good overall understanding of the system, and functional decomposition is very useful with that. So let's look at this example of an auto shape. So again, breaking it down in terms of functionality. So we have the auto shape feature. What can it do? So the sub functions that it provides are there's the click functionality, so you can click on the shape and select it. So that's the mouse click. You can change the shape, so you can basically select it and drag it to change its size or its position even. And then there is the ability to draw the shape. So you basically are able to select a shape and then draw it on the editor. So we've broken down our overall auto shape feature into 3 smaller sub functions. Now, can we further break it down? So basically changing a shape, what does that involve? So again, depending on the type of shape, the change functionality is going to vary. So are we changing a rectangle, or are we changing an oval, or are we changing a circle? And based on that, we have to have specialized code. For rectangle, we're going to use the features of a rectangle in order to provide the ability to change it, and similarly for an oval and a circle. So those are our smaller sub functions of change. Similarly for draw, it can be further broken down into draw rectangle, draw oval, or draw circle, because the overall ability is to draw, but then in order to draw a rectangle, we need specialized code with the say the width and the height of the rectangle, and draw it appropriately. Similarly for mouse click as well. So basically the idea is, again, to start out at that high level single function, break it down into smaller functions, further break it down into smaller functions, keep doing that till we get to the smallest possible function. In this case, say draw circle, draw oval, draw rectangle are those smallest subfunctions. Maybe they can be broken down further. But then again, what is the purpose that we're doing this for? If it's for design purposes, then maybe stopping at that level is fine, because it gives us a good understanding of the system that needs to be built. Next, we'll look at object decomposition. So here's a picture. I'll pause on this for a couple of seconds. I want you to think about this picture and what is this? What do you see? Now, typically I get different answers. There's multiple things one could see in this picture, and it's all up to your interpretation of what you see. So if I were to give you this picture and say, now a design for this, to create something like this, and say the design methodology is object-oriented design, so I want you to come up with classes and properties, then it would be up to your interpretation to decide on what those classes and properties would be based on what you see. Now, say for example, say this is an Eskimo. Say what you see here is an Eskimo. Then what we're seeing is basically here's the elbow of the Eskimo. So basically it's an Eskimo, say, entering a cave. So if that's what we see, then so there's the elbow, there's the neck of the Eskimo, here's the glove in his hand, then there's the pocket on the Eskimo's jacket, and then here's the cave into which the Eskimo is entering. So, so if that's the interpretation, then based on that, if you were to model it, then we would model this as an Eskimo class, right, with attributes and behaviors that are specific to an Eskimo. Now, there could be other interpretations. What if you see a face or a head, basically a head, maybe a head of an Indian? So in that case, what we're seeing is basically a nose, a mouth, a chin, there's a ear, eye, and hair. And with this interpretation, if we were to model what we see, then we would come up with a class head, and then all of the properties of a head and behavior of a head. So so it's totally up to our interpretation, and then we continue with the modeling and decomposition based on that. So it could be anything. I mean, an Eskimo or a face, because there's both of them are correct. One could argue that both of them are correct. So this is where in the real world, in the software world, this is bound to happen. There could be multiple interpretations for the same thing. It's very important that we try and get clarity on our interpretation and verify if our interpretation is correct or not by talking to the client. That's the reason there is a detailed requirements analysis phase, and that's what we usually begin with. It is an iterative process, so we make sure that our interpretation of the problem specification is correct. So in this case now, if we want to model an Eskimo, then here's how our model would look. So what I'm showing here is a class diagram. So we are basically creating a class called Eskimo. That's our class name, and then this class has attribute size. So there is a size, and then here's our behaviors. So the Eskimo can basically dress up, Eskimo smiles, Eskimo sleeps. So those are the attribute, the behaviors or the methods that we come up with. Now, in addition to that, next we might want to model more details about the Eskimo. So the Eskimo, say, wears shoes. The Eskimo can wear multiple shoes, so there's that multiplicity symbol. Now, this notation that I'm showing here is UML notation, Unified Modeling Language. It's a class diagram. It's a way to create object models, and we will look at this in detail in the UML lectures. Now an Eskimo could also have a coat, and then the coat has certain attributes, certain behavior. Similarly, the shoe has attribute, size, color, type, and behavior is that it's worn. So Eskimo wears the shoe. So and then further iterative modeling. So basically we start out with that high level class, which is Eskimo, and then what is the Eskimo wearing, and then what are the surroundings of the Eskimo? The Eskimo lives in a cave. The cave has multiple entrances. There's different types of entrance. There is a main entrance and there is a wind hole entrance. So all of that can be modeled using UML. So there's here's the entrance, which is a generic object, and then there's two specific objects, main entrance and wind hole. Now the Eskimo lives in a cave, so and the cave has certain lighting, and then one can enter the cave and leave the cave. So those are the behaviors. So through iterative modeling, we basically add more detail to our model. So we start at that high level class, and then further think about, break it down further, and get into the more smaller classes that are associated with it, and also come up with those associations. And that's what we're doing here in this iterative modeling. So in addition to where the Eskimo lives, the Eskimo moves around outside. So what are the properties of this outside environment? What's the temperature like, what's the lighting like, and what's the season, and then what does the Eskimo do outside? So those are the behaviors. He or she hunts, or they organize and get together and do something. So that's some additional behavior of the Eskimo. So but then going back to the question, is this the right model? So like I said earlier, it's all up for interpretation. If we saw, when I showed you that picture, if you first thought that it was an Eskimo entering the cave, and if that is indeed the client's expectation as well, then yes, this is a correct model. But then if that's not what the client's interpretation was, then we have a completely wrong model over here. So again, it's very important that we make sure and know what the client's expectation is. So if this is the head of an Indian, then it's basically our classes would look different, our object model would look different. In this case, we would have a main class called Indian with properties, hair, and then behavior, dress, smile, and sleep. The Indian's head is made up of a face. The face has a nose, and then the ability to smile and close eyes. Then the face comprises of a ear, the size of the ear, and the ability to listen. Then the face also has a mouth. On the mouth, there's properties, number of teeth and size. And then the mouth can be open, and one can speak with it. So all of those. So you see, everything changes now. The entire model has changed, and again, through an iterative modeling, we can add more detail to it. But then, before we get too far, we want to make sure that we have the correct model, and that's where we basically confirm that by making sure that we have understood the specification correctly. So class identification is crucial in object-oriented modeling. That's the very first step. That's what we start with. Now our basic assumption is that we can find so whenever it's a new software system that's being built, we're starting from scratch, so we can find these classes and it's basically what are the important key concepts in the system, and what are those real world objects that are needed, and how do they interact with each other. So that's what's called greenfield engineering, wherein we start from scratch to building a new software system. Now it could be that it's a re-engineering task wherein we're working with an existing system, and in that case we need to again identify classes from an existing system, and that's re-engineering. Or it could be interface engineering, where the system, there is a class-based interface to any system. It's UI, user interface heavy, or there's other kind of interfaces where that are being connected with other components. So there we're thinking of classes in terms of those interfaces. Now either whichever technique that's being followed, be it greenfield engineering or re-engineering or interface engineering, class identification is that first crucial step that has to be performed, and it's important that it's done correctly. Now some background on object oriented technology. I'm assuming all of you know this already. You've done it through other courses because it is a prerequisite for this course. Basically the idea is, again going back to the definition of software engineering, we are using existing techniques, existing methodologies and tools to produce high quality software. So basically this methodology is this process of organized production of software. So we're going to use a collection of these predefined techniques and notational conventions. So with object-oriented technology, there are these set of predefined techniques of how the programming is done, and the notation is basically provided through the programming language that's being used. There are a number of different object-oriented programming languages. Java is one of them that you've been exposed to, but then there's others as well, a number of other ones like C#, there's C++, and so on. Any of them can be used, but that's they're providing the notation through the language syntax. So object-oriented methodology is basically this approach where the system is a collection of objects that contains both data and behavior, and we are building the system using these collection of objects. So that brings us to the question, what is an object? And that's it's important to understand that. So basically an object has a structure, so it has some attributes, and so that's the data part, the data that's held in the object. And then it must be an entity. It is a thing, it is a concept, and it can have certain properties or attributes. Now it cannot be the property itself. It should be a thing that has some properties. So and then it also has some behavior. So typically that's what an object is, and an object always has a unique identity as well. So and generally it's stated as a noun. You will see that an object is always stated as a noun. So to give you an example, thermometer is an object, and temperature is a property of thermometer. Now temperature is not an object, it's a property, it's an attribute of the thermometer. So think of it in terms of nouns. Anything that can be stated as a noun is a good candidate to be an object. So basically objects must have attributes, must have behavior, and then they have a unique identity. Now this picture here, what is this? What do you see? So I think the obvious answer that would come to your mind based on that picture is that it's a briefcase, right? So if you were to model this, then you would create a class called briefcase, right? And then provide some attributes to it, its properties basically, by saying that capacity, the briefcase's capacity, its weight. So those are two good attributes. And then we need some behaviors for it. So our behaviors could be that the briefcase can be opened, it can be closed, you can carry it around. So those are our behaviors. So that's how we would begin to model it. That's our high level, very first thing that comes to the mind. We give it a name, give the class a name, identify some attributes, identify some behaviors. Fair enough. Now say we find out that there is a new use for this briefcase, and that new use is that one can sit on it. What that means is now we'll have to add a new behavior called sit on it. Fine, we've added that. Now so I told you object modeling, it's an iterative process. So we continually add to it, but at the same time as we are going through this iterative process, we need to keep asking the question, is this the right object? Is this the right model? Do we have we interpreted it right? So it's always we have to keep asking those questions again. Now, why did we model this thing as a briefcase in the first case? Because the picture, that's what it showed, right? It looked like a briefcase, we modeled it as a briefcase. Now, why did we not model it as a chair? Well, it did not look like a chair, right? Based on that initial information, it looked like a briefcase, so we modeled it that way. Now, so we've identified that the operations are open, close, carry, and then sit on it, because we were told that that's the new use for it. Now, what if we find out that sit on it is the most frequently used operation? That's the key operation. Now, does that make sense? Like a briefcase, the purpose of the briefcase is not to sit on it. So, so that's where we think about it further. Now, say we find out, based through further analysis, further brainstorming, we find out that the purpose of this object that we're modeling is mainly to be sitting on it. It is never going to be opened or closed. If with that said, then did we even model it right in the first place? Is it even a briefcase? Maybe it should be a chair, because you typically sit on a chair, and we've just found out that this object can never be opened or closed. We're not going to use that functionality. So the moment we find that it's a modeling mistake, we want to fix it. We make sure we fix our modeling mistakes as soon as we find them. So again, to drive the importance of basically, we're using object-oriented decomposition, which means identifying objects, breaking them down into smaller objects, and get to the smallest level possible. That's good. Now, given the specification, we're trying to identify objects in the best possible manner. We start at the high level with the high level objects, and then try to add more details to it through an iterative process, through an iterative modeling process. But as we are doing this, we want to make sure we rethink and think back, look back at the specifications, and make sure we're doing the modeling right before getting too far. And if we find that there were mistakes in the way we were thinking, we fix it as we go. Always a good idea to check back with the client to verify, to show our design, whatever we have so far, and make sure that we have understood the problem correctly. So let's do a few quick exercise here. Say you're given the task of designing for a particular system, then how do you go about identifying the objects? What are the objects that are likely to be encountered in these systems? So the first system is a convertible car. So the moment we hear convertible car, so we obviously think of the car's engine, the doors, the seats, the hood, the trunk, so all of the different parts of the car. Those are, so that's how we start out with this process and come up with all of the high level objects that we can think of for the particular system. Now, if it's an airline, then the objects that come to our mind are the airplane, the terminal, the baggage claim, schedule, tickets, reservation, pilots, flight attendant, and so on. For a computer network system, basically we think of files, protocols, server, workstation, cables, ports, routers, and so on. So that's how we come up with a list of potential objects first that are relevant to that domain. And then from there, through an iterative modeling process, define further detail and take it from there, go through building an object model. Now, with object-oriented concepts that you're familiar with, but just as a quick refresher, now what is a class? So basically, a class is a group of objects, a group of similar objects, right? These objects have similar kind of properties or attributes, they have similar behavior or operations, they have the same kind of relationships to other objects, and then they have the same common semantics. So that's when we're grouping them into a class. So this class is basically like a template where we're defining how the objects of this that are belonging to this class look. They all have similar properties. So what are those properties? They all have common behavior. What is that behavior? They all have the same kind of relationships to other objects. So what are those? And so they all have this common semantics that's defined through these properties, behavior, and relationships. So that's what is it's a class. Now, what's the difference between a class and an object? Now, a class is just the template that's bringing all of these similar objects together. An object is the actual thing. It's the instance. It's an instance of the class. It's the actual instance that contains the data. So it has some data. For each attribute, there's certain values. If this attribute's color, height, weight, all of them is going to have real data. The object is going to have its own unique identity. So the object is actually an instance of the class. So it's very important that you make sure you understand the difference between a class and an object. Here's our second exercise, wherein we are given some objects and we have to identify the class that it belongs to, that these objects belong to. So the first one is a 747 Learjet twin engine plane stealth bomber. So these are objects. Now they all have certain similar properties that you can see from the name. So it's basically we can put all of them into a class called airplanes. So they're all similar objects that can be grouped under this class called airplane. Now the second one is laser printer, dot matrix printer, inkjet printer, fax machine, photocopier. So all of them can be grouped into a class called, say, printers. The third one is fog light, headlight, blinker, brake light, backup light, turn signal. So basically these can be grouped into a class called, say, a light or a motor vehicle light or an auto light. So basically it's again grouping it to come up with a class. So now that we have seen decomposition and how we can do a functional decomposition and object-oriented decomposition, the third way to deal with software complexity is hierarchy. So now here we have broken down, we have all of these chunks, smaller chunks. We want a way to provide some relationships between these chunks, and these relationships can be in the form of a hierarchy. So there's two different kinds of hierarchies that we'll look at, part of and is kind of. So basically part of is there is a whole and we're breaking it down into smaller parts. So a good example is a computer. A computer is made up of I/O devices, it's made up of CPU, it's made up of memory. So a computer can be broken down into these three parts, or we can say CPU is a part of computer, memory is part of computer, I/O devices are part of a computer. So that's the part of hierarchy. Now CPU can be further broken down into cache, ALU, and program counter. So cache is a part of CPU, ALU is part of CPU, and program counter is part of CPU. So this arranging chunks in this manner where there is this part of relationship is called the part of hierarchy. Now another way to do it is the is kind of hierarchy, wherein this is like inheritance, wherein you have a more generic object and we derive specific objects out of it. So for example, cell is generic cell, but then there could be specializations of cell, say a muscle cell, blood cell, or a nerve cell, and then the muscle cell can be further broken down into striate and smooth. Blood cells can be broken down into red and white. Nerve cells can be further broken down into a specialization called cortical and pyramidal. So here this is a is kind of hierarchy, wherein we are taking a generic type, breaking it down into more specific types. The blood cell is of kind cell, a muscle cell is of kind cell, and so on. A white blood cell is of kind blood cell and is also of type cell. So that's the is kind of hierarchy. So basically what we looked at is 3 different ways to deal with complexity: abstraction, decomposition, and hierarchy. And then we also saw that decomposition can be done either through object-oriented decomposition or functional decomposition, and both of them, it's a good idea to apply both. Now, what do we do next? So basically, with these approaches, our idea is to start out and do the modeling, describe the functional models, describe the object models, and describe the dynamic models. And typically that's done using UML modeling language, and then that also leads us to a certain kind of process, and that process can be studied through software life cycles, which you will see in the follow-on videos. Thank you.